stay in time. We have still the large study in the assembly. Actually, yesterday we touched it. Today it's a continuation of the clinical ribosome assembly with 5 talks. My main function is to watch the time, and therefore I would like to hand over to Dieter. And he will talk about co-translational capturing of nascent ribosomes produced by their dedicated chaperones.
So thank you very much, Ed. So first I would like to thank the organizers for giving me the opportunity to speak about our recent work on dedicated chaperones of ribosomal proteins. In the first part of my talk, I will show you some evidence that dedicated chaperones recognize ribosomal proteins as these are synthesized on the ribosome already. And if time permits, I will show you some unpublished work which we identified another dedicated chaperone that escorts ribosomal protein L4 to its nuclear pre-60S assembly site. So as you all know probably, most ribosomal proteins need to travel from the cytoplasm where they're synthesized across nuclear pore complexes to their nuclear assembly sites at pre-60S or pre-40S or 90S pre-ribosomes. But however, ribosomal proteins have difficult physical-chemical properties. Many of them are highly basic and have unstructured regions, and hence they're prone to aggregation when they're not associated or integrated into their cognate ribosomal RNA surrounding. Therefore, they need to be they're required to be protected from their synthesis onwards until their pre-ribosomal incorporation. So, 10 years ago, it was shown by the Görlich lab that importins not only mediate the transport of ribosomal proteins, but they also fulfill a role as chaperones of ribosomal proteins by preventing their aggregation in the presence of polyamides. So, besides that, and more importantly for us, there are also specific binding partners of ribosomal proteins that contribute to the efficient synthesis of assembly-competent ribosomal proteins, and we have termed this class of proteins dedicated chaperones. So we became interested in dedicated chaperones a few years ago when we observed that a protein named symportin, or briefly CO1, simultaneously binds to 2 ribosomal proteins, RPL5 and RPL11. You've heard about that from Irmi yesterday. Thus forming a trimeric complex which is imported into the nucleus by interaction between CO1 with the importin catenin 4, and this couples the transport of RPL5 and RPL11 to the assembly of a pre-5S RNP intermediate, which is then transferred onto the pre-60S subunit. So, briefly, the study at the time has discovered that symportin is besides being a chaperone mainly for RPL5, another transport adapter, or a specific transport adapter that's structurally and functionally similar to the classical co-importin alpha. And also, you have to keep in mind is that what we could show is that CO1 recognizes the first 20 amino acids of RPL5. So at the time there was another dedicated chaperone quite well characterized, it's YAR1. You've heard about that from Brigitte yesterday. And YAR1 is an uncurrent repeat protein which protects RPS3 from aggregation. And structural as well as binding studies on structure has been solved by Sebastian Klinge. And our binding studies revealed that YAR1 binds to roughly amino acids 14 to 29 of RPS3. So the starting point was that we concluded that both the 2 well-characterized dedicated chaperones, CO1 and YAR1, both recognize the internal parts of their ribosomal protein partners L5 and S3. But that's why we had the obvious question, do other proposed dedicated chaperones also interact with the internal parts of their ribosome protein partners? So at the time it was known that there are 2 additional proposed dedicated chaperones, which is RB1 and SQT1 for L3 and RPL10. So it has been shown that SQT1 interacts with L10 and promotes its loading of the pre-60S subunits. I was working with Trumpauer and Johnson Lab. And as you will see in a minute, SQT1 is an 8-bladed double repeat beta propeller. On the other hand, RB1, which is a predicted 7-bladed beta propeller, was shown to interact with L3, and it may accompany L3 from the cytoplasm to its nuclear-free 6-gas assembly site. And that's what you can see in their position in mature ribosomes. The N-terminal parts of L3 and L10 interact with ribosomal RNA, and they're buried inside the 6-gas core. So as suggested by previous studies then, we first addressed whether SQT1 and RB1 are indeed specifically associated with L10 and L3, and as shown here in tap purifications of these two proteins. So SQT1 yields good co-enrichment and exclusive co-enrichment of L10, and RB1 exclusive co-enrichment of L3. So then, next step was to identify their binding sites on the ribosomal proteins. To make a long story short, we could show that the first 20 amino acids of L10 interact with the beta propeller domain of SQT1, and that the first 15 amino acids of L3 interact also with the beta propeller domain of RB1. To confirm these two hybrid data, we performed in vitro binding assays, so we co-expressed L10 and SQT1 and purified L10. And you can see that in this purification you have stoichiometric amounts of SQT1, and then also just purifying the first 20 amino acids of L10, you could co-purify full-length SQT1 or the beta propeller domain. So we can conclude at that point that SQT1 binding site resides within the first 20 amino acids of L10, and the RB1 binding site is within the first 15 amino acids of L3, and that the beta propeller domains are sufficient to accommodate these N-terminal regions of the ribosomal proteins. So next we wish to understand the interaction mode between SQT1 and the L10 peptide. So I have to say that for RB1 you could not do it because RB1 is expressed as large as an insoluble protein in E. coli. So we focused on SQT1. So we collaborated with the lab of Gerd Bange, and his student Patrick Pausch could solve the crystal structure of S-terabese SQT1 beta propeller and the co-structure between the beta propeller of SQT1 and the RPL10 N-terminus. And so what you can see here is that the SQT1 is a negatively charged top surface which accommodates the RPL10 N-terminal peptide. And having a closer look at this interaction, you can see that so this would be where the N-terminus of RPL10 lies in the mature 6-gas. So it interacts with helix 89 here, it's inserted here. And this is very similar on SQT1. So SQT1's top surface mimics the L10 binding site on helix 89 of the 25S rRNA, and most likely thereby it prevents RPL10 from interacting with this helix 89. So this is just a slide to demonstrate that we also validated the crystal structure. This is a linear representation of the interaction mode, and you can see that there are mainly 3 basic residues, arginines of L10, that mediate important ionic interactions with 4 negatively charged residues on the beta propeller surface of SQT1. So first we just performed simply 2 hybrid analysis. We mutated the SQT1 residues, and we could show that substitution of these negatively charged residues to positively charged lysine residues reduced or abolished the interaction with RPL10. This also correlates with their growth phenotypes in vivo. So you have a slow growth phenotype for the ones that interact with reduced interaction, and lethality for the ones where interaction has been lost. And also, similarly, when we mutated these arginines on L10, we reduced or abolished the interaction with SQT1. So our study also provided additional evidence that SQT1 can be considered as a chaperone of RPL10. first in vivo, as I've just showed you before, SPT1 is exclusively associated with non-ribosome associated or non-ribosome bound RPL10. We also observed very striking allele-specific synthetic lethal interactions. So only by touching two different interaction pairs, cells are unviable, shown here. And more importantly, we could also show that overexpression of L10, so providing more L10 in the cell, bypasses and is suppressing those SPT1 mutants where interaction is reduced. So we have a complete suppression here, and we can even bypass the requirement for SPT1. So these are cells where SPT1 is absent, and more RPL10 leads to viability. In agreement with this, we could also show that when we induce the expression of a tagged L10 in SPT1 mutant cells, we had barely soluble L10, but by providing at the same time SPT1, we had a soluble pool of RPL10. So it increases the solubility of this RPL10 protein. So next we wanted to follow this intuitive possibility that due to the recognition of the N-terminal residues that this recognition might already occur when ribosome proteins are synthesized by the ribosome. So to this end, we applied a very sensitive method which couples chaperone purification to the detection of specific ribosome protein mRNAs by real-time PCR. So briefly, we treated cells prior to harvesting cyclohexamide and also include that in cell extraction to freeze polysomes and preserve polysomes. Then perform the IgG Zephros pull-down step, followed by TEF cleavage to release the tag chaperone and associated proteins and the mRNA, if possible, followed by RNA isolation, cDNA synthesis, and then real-time quantitative PCR with different oligonucleotide pairs detecting different ribosome proteins, mRNAs. And this now showed that in all cases, purifying RB1, CO1, SPT1, or YAR1, we observed a 25 to 100-fold enrichment of the specific ribosome protein mRNA, so L3 for RB1, L5 for CO1, etc. So we conclude that all 4 dedicated chaperones that we have tested recognize the specific ribosome protein partner in a co-translational manner. So I would like to conclude this part of my talk with a model of the SPT1 assisted assembly path of L10. So SPT1 recognizes RPL10 when it is synthesized on the ribosome in the cytoplasm. This complex will then dock onto a cytoplasmic pre-60S subunit, and which already contains, this is elegant work from the Johnson lab, this step contains NMD3 and LSG1, and then by the action of LSG1, NMD3 can be released, RPL10 will stably dock or stably bind, and SPT1 is released. I have to say that this initial docking step of the SPT1 L10 complex is not really clear to me how this will occur, because the binding sites for NMD3 and L10 are partially overlapping, as shown in the work lab. NMD3 binding sites, and they are overlapping with helix 89 and helix 38 binding of L10. So we postulate that initial binding of SPT1 bound L10 might involve the base of helix 38 or the C-terminal extension of RPL5, which is also eukaryote specific. So in conclusion, the study has allowed to define a novel ribosome biogenesis step, which is the co-translational capturing of ribosome proteins by their dedicated chaperones. So while our study was progressing, 2 additional dedicated chaperones were identified so TSR2, as we heard, from Vikram Panse, governs the nuclear transfer of S26 from the input into the 90S pre-particle. And the work lab and our unpublished work identified ACL4 as a protein that escorts RPL4 to its nuclear pre-60S assembly site. So if time still permits, I will just 2 minutes. So I'll briefly show you some evidence that we have for that. So RPL4 is you will hear more about that from Ed, is a very remarkable protein. It has a long C-terminal extension that spans across half the width of the solvent side surface of the 60th subunit, and also has a long internal loop which penetrates from the surface to the exit tunnel where it forms the constriction point. So we first simply tested whether this extension of the loop is their role for the functionality, and we can show that the deletion of these parts abolishes growth of these cells, and also we observe a dominant negative effect on growth by just expressing L4 that lacks the C-terminal extension. This protein also localizes partially to the nucleus, so we hypothesized that it might be associated with pre-ribosomal particles. And by doing this purification, we could show indeed that there are some early pre-60S factors, but we also observed a prominent band which contains a protein which is termed by ETSLab ACL4. And by doing the reverse purification of ACL4, we could co-purify L4 and the degradation product thereof. So first we were interested to see where this ACL4 binds to RPL4, and we identified a major binding site on the C-terminal part of this long internal loop. And we confirmed that by performing a mutation analysis, so consecutive alanine exchanges, and all of these mutants abolish the interaction with ACL4. And also, it's shown in vitro binding assay, co-purification of RPL4, ACL4 with RPL4 bait, and by mutating these 4 residues here, we lose the interaction. So confirming that this part of the long internal loop is a main binding determinant. So, as before, we also checked whether ACL4 could be a dedicated chaperone of RPL4. So we observed dosage suppression, so the slow growth phenotype of ACL4 non-mutants is completely suppressed by increasing amounts of RPL4. We also observed synthetic enhancement phenotype, so cells that lack RPL4A copy and ACL4 are substantially sicker than the 2 single mutants. And finally, we could also show that lack of ACL4 reduces the solubility of RPL4 in these cells. And then we also performed our chaperone pull-down RT-PCR experiment, and as shown here, ACL4 tap specifically enriches the messenger RNA of L4, but there's no L3 as a control, or L5. So this leads me to the model we have for the ACL4 dependent assembly of RPL4. So ACL4 as well has the capacity to recognize RPL4 as it is synthesized on the ribosome. This trimeric complex is recognized by an import team, most likely Cap104, which binds to the C-terminal region, C-terminal extension of RPL4. This mediates the import, and then we don't know exactly what's happening, how this RPL4 is integrated into the pre-60S subunits, but I guess Ed will tell you more about that. So with this last slide, I would like to acknowledge the collaborators. So the crystal structural work has been mainly done by Patrick Pausch in the lab of Gerd Wange. Yazar is the collaboration with Matthias from the Sitting and Hort lab. They also independently solved the crystal structure of SVT1. And in my lab, it was the work of Ujjwala and Benjamin for the functional aspect of the co-translational recruitment story. And Benjamin has a poster on the ACL4 story. That's poster number 140 if you still would like to see it. And he was helped in the lab of Jesus who did some RNA analysis for us. So, thank you for your attention.